Okay, so the next presentation is on a novel and integrated methods for SDB to extend the geographical potential, improve data accuracy, and through cloud computation, produce satellite derived bathymetry, or SDB, at scale not previously envisioned. So we will have two presenters to introduce. Kyle Goodrich will introduce the presenter. Corey Goodrich will introduce the presenter, Kyle Goodrich. Kyle has a 20-year career in remote sensing and hydrospatial services and a degree in geosciences from Williams College. Since founding TCarta in 2008, Kyle led numerous product research and development plans, including the commercial of satellite derived bathymetry, shoreline classification, global bathymetric products, and 2 small business innovation research grants from NOAA in US and the National Science Fund in US as well. Donc, sans plus tarder, nous pouvons démarrer. Corey.
OK, merci beaucoup. Vous pouvez m'entendre?
Oui, très bien.
Oui, merci. Bonjour, merci beaucoup à Sidco et à vous, Denis, pour avoir accepté la soumission de TCarta afin de présenter ici aujourd'hui. C'est un vrai plaisir de participer à cet événement important. Je m'appelle Corey Goodrich. J'ai été récemment nommée comme curatrice de la Société hydrographique de l'Amérique aux États-Unis, THSOA. Je suis aussi une propriétaire et une associée gérante à TCarta Marine, une compagnie expérimentée dans l'industrie hydrospatiale. TCarta a été fondée il y a 15 ans et nous avons 12 employés principalement à Denver, Colorado. Nos performances passées incluent des projets fournissant de la bathymétrie par satellite avec UKHO, NOAA, le Service hydrographique du Canada et plusieurs autres agences internationales, particulièrement au Moyen-Orient. Au profit de notre spécialisation en bathymétrie satellitaire, depuis 2018, TCarta est engagé dans 2 subventions fédérales américaines avec le NOAA et le NSF. Ces subventions fédérales financent la majorité de nos développements technologiques en matière de bathymétrie satellitaire. En particulier, les progrès avec iSat2, l'apprentissage automatique et la fusion de capteurs. Avec des initiatives comme the Nippon Foundation GEBCO CIBA 2030 et la décennie des sciences de la mer de les Nations Unies, la bathymétrie satellitaire est devenue un élément commun parmi les solutions aux problèmes hydrospatiaux mondiaux. En termes d'échelle, d'harmonie de plusieurs capteurs et d'application d'apprentissage automatique pour le traitement de données à haute densité, la technologie de bathymétrie satellitaire arrive à maturité. Ce n'est pas un hasard que cette maturité de la technologie se manifeste en ce moment, alors que l'industrie hydrospatiale a besoin de solutions ayant une couverture variable en fonction des besoins. Il me fait maintenant plaisir de vous présenter Kyle Goodrich, président et fondateur de TCarta. Il vous présentera en anglais la technologie de TCarta pour les besoins en hydrospatial. Kyle.
Bonjour, merci. Bonjour, merci. I'll continue in English. Thank you. Yes, I'm going to speak on our satellite derived bathymetry at scale and our new methods in automation and where kind of TCarta fits in the hydrospatial world. First, I thought I'd give a little bit of an origin story around satellite derived bathymetry to kind of set the setting for how satellite derived bathymetry has evolved over time. And ultimately, this goes back to the early 1970s with the world famous Jacques Cousteau was one of the first people to calculate water depths in the Bahamian region. It was a carefully orchestrated event, including satellites, aircrafts, ships, and divers, all coordinated to calculate water depths. But ultimately, this was the inception point of satellite derived bathymetry, and they were able to calculate water depths to 22 meters in the Bahamas. And ultimately, a lot of this physics-based approach, physics is physics regardless of the time. So a lot of this math is still valid today. And what's really evolved is satellites and development of algorithms on top of these physics-based concepts. That's really what's evolved satellite derived bathymetry over the years. So if we just looked at the next 20 years of satellite derived bathymetry, it was actually kind of stagnant through the 80s and 90s. There was some uptake by Schoen, as we all know, in the 90s, and started putting satellite derived bathymetry on charts. But as you might expect, satellite derived bathymetry really is hinged to the availability of satellites. So during this period, there were a number of new satellites being launched, largely by government agencies, and they became available, but they weren't really yet commercialized or yet quite quality enough to produce satellite derived bathymetry to meet the needs. But then at the end of this period, in the late 1990s, we saw kind of the beginnings of the commercial space industry with the launching of some OrbView and Iconos in the late 1990s. And this really began the dawn of having high resolution, commercially available satellites to complement the government operated more coarse resolution satellites. And then through the 2000s, we really saw the dawn of high-resolution satellite imaging. WorldView 2 was launched in 2009, and here we are, 2021, and it is still the premium sensor for satellite derived bathymetry. And Mark mentioned earlier the radiative transfer method, and this during this period, this is when the radiative transfer method really got established and became kind of the premium approach to producing satellite derived bathymetry. But then also the increase of computational power was a big detractor, previous to this, because this needs significant computational power to process high-resolution satellite imagery to produce satellite derived bathymetry. There was also some initial uptake by hydrographic offices at this period, starting to use commercial providers of satellite derived bathymetry, TCarta being one of them. And as well as, as I said, there's an establishment at this point in the 2000s of some of these early commercial providers of these products and offering products to governments and to industries. We fast forward the next decade, in 2010 through 2020, I like this Hydro International article in 2015 that says SDB came of age, or was coming of age in 2015. And I largely agree with that statement, though while it came of age, it still has some limitations, largely around being able to validate the results of bathymetry. Yes, you can calculate water depth, and now we can get uncertainty and CAT-SOC levels at this stage, but largely it still required mobilization of an aircraft or a boat to go out and survey and validate the results in order to know that you're getting good satellite-derived bathymetry results. So that still had a little bit of a detractor from actually the large-scale proliferation of the technology as I personally see it. We also saw the proliferation of more higher resolution satellites during this period, and the ability to image areas on a sub-daily or to a daily basis using planet imagery. So we're now able to view the world in much higher resolution, the hydrospatial world in much higher resolution, and also more frequently with all of these satellites. And now the technologies are starting to kind of evolve along with them. But I see that where it really came of age was in 2019 when ISAT-2 was launched by NASA. This was an active sensor in space. So all the previous sensors I'm talking about are Earth observation, observing reflected light off the Earth. In this sense, this sensor, we're pulsing a laser at the Earth, a green laser, a 532 nanometer laser, so similar to an airborne aircraft LiDAR approach. But what this does is allow us a secondary method, using a secondary sensor, to validate the satellite derived bathymetry that we're producing from optical satellites. So this really allows us to put this in as a stand-in for ground truthing. So we're no longer needing to be like Jacques Cousteau and deploy divers and ships to an area in order to validate. We're able to validate using this space-based sensor that is just going around the Earth every 90 days, collecting data over the same area. So we're able to get repeat collection over the same area, and then fuse that data with the Earth observation sensors. And that, to me, was when satellite derived bathymetry really started to come of age. So what can we do with these capabilities? Both the high resolution satellites with targeted and precise multi-sensor high resolution tasking. And then we also have a different approach of kind of regional and global scalable data sets that leverage multi-sensor collections that are going on nominally, so we don't actually have to task imagery. These images are just being collected and put into archives that we can just access and process. So two different approaches that I'm going to just kind of briefly touch on. And here's an example of a high resolution tasked project. Excuse me. So this is a high resolution project. We tasked WorldView 2 and WorldView 3 over this area in Cape Cod in the summer of 2020. It's a really challenging area to do satellite derived bathymetry because it's unconsolidated seafloor, very sandy, and lots of strong currents and tidal currents causes a lot of turbidity in the area. So we work quite closely with the satellite operators or Maxar specifically, to collect over 55 images for this project. You can see kind of the cadence of collection from June 1st all the way till almost November 1st last year. We collected 55 images, and this is with custom collection parameters to optimize satellite derived bathymetry. But ultimately, we can optimize it when things happen on the sensor all we want, but we can't affect clouds and turbidity that are in the environment. So ultimately, we need to collect many images in order to get clear water conditions. As you can see, in some of these areas, we got up to 15 images repeated over time in order to get good water conditions. So that's something we can do with high resolution and really be precise about tasking these satellites and using custom parameters to optimize this for satellite derived bathymetry technology. Because it's worth mentioning that all of these Earth observation satellites to date are traditionally calibrated for terrestrial remote sensing, not marine remote sensing. So we're now able to parameterize some of these satellites for marine applications specifically and able to enhance our capabilities much further. So if we take kind of the other approach, scalable and regional global satellite derived bathymetry, that's where TCarta's National Science Foundation grant has really accelerated our development here to look at broad areas of potential for satellite derived bathymetry, as well as entire archives of satellite images, including Sentinel, Landsat, and then also commercial providers. We can start to look at automating these processes and getting one process to inform another and to validate another one. So we start to be able to combine these processes together. Is really when it can get interesting. So how do we combine things? We can take a single image potentially and run it through multiple algorithms to produce satellite derived bathymetry. Mark had mentioned earlier the radiative transfer method. That is the premium method, but no one method works in all places at all times. So we've kind of taken a philosophy of all of the above for satellite derived bathymetry algorithms, using a random forest classifier and then the traditional band ratio, similar method that they were using in Jacques Cousteau's time, but physics is physics, and it works. But ultimately, because we're able to use the computational power has gone up tremendously, we're able to compute in the cloud now. We can calculate hundreds, thousands of times at virtually no cost. So why not take an all of the above approach when it comes to algorithms? We also have kind of a plethora of satellite images to choose from. This is just taking a look at the Sentinel-2 imagery back to Cape Cod here, Martha's Vineyard in Nantucket. Just through a simple filtering of an archive of a year's worth of satellite images from Sentinel, you can see that this is just the best of the best of images that were filtered by cloud cover and various environmental conditions, but kind of in a crude way. But we can take all those images and get it down to 7 or 8 best images from the year. So what can we do with this? We can take each of those individual images and then process each of those individual images through multiple algorithms to produce satellite derived bathymetry. We can then also take in those individual images and combine them into multi-temporal composites and process them through multiple SDB algorithms. So then we can also take various combinations and compare, so we can look at what does it look like in the first quarter of 2020? What does it look like in the summer of 2020? And what does it look like from July year to year to year? So you can see the combinations become somewhat endless in terms of how you can combine these satellite images to start to get an understanding of not just the bathymetry depths, but how the bathymetry depths change over time. And that's one of the big powers of satellite derived bathymetry is we can actually go out and deploy, quote unquote, satellite derived bathymetry in 1990, back in time, because we can go back in an archive and see what it looked like in 1990, and then process it from today's imagery and compare the results. You can't do that with a multi-beam survey or a LiDAR survey. You can't go back in an archive. So that's one of the big powers of satellite derived bathymetry, and being able to combine these and optimize the results. Now, we're also now at the age of, we can look at sentinel imagery every 4 to 5 to 6 days, depending on where you are in the latitude, and get a fresh image by doing nothing, just looking into the archives to be able to see every 5 days there's going to be a new image that comes in that we can evaluate for the feasibility of satellite derived bathymetry. But sometimes that's not high enough temporal repeat for satellite derived bathymetry because the environmental conditions change considerably from one day to the next. So you can combine this now with a commercial provider of planet imaging, where with a planet scope, you can get daily to sub-daily imaging of a location at 3-meter resolution. And then you combine that with the ability of a planet plugin to bring it right into Esri's ArcPro software. You can download a satellite image right into your hydrospatial software, use a satellite derived bathymetry algorithm that TCarta has put all of our algorithms in Esri platform to process it. You can actually collect an image, process satellite derived bathymetry within minutes, as opposed to going back to Jacques Cousteau from 1975, who took weeks of planning to go out and try to orchestrate the satellite derived bathymetry. So a lot has changed. And of course, it has been 45, 46 years since Jacques Cousteau's era, but a lot has changed in this, that we are now able to almost go click button from satellite imagery downloaded to my computer, process satellite derived bathymetry, get uncertainty, CATSOC levels, put it into a data standard of a bathymetry attributed grid, get it into an interoperability situation where you can deploy this data to your marine operations or your aircraft operations, and almost seamlessly from satellite to the marine environment, get bathymetry to those who need it the most at the right time. So quite a lot has changed in this technology over the last years, and in my mind, really starting to accelerate. So we can also look at processing large regions of satellite derived bathymetry using cloud computation. We can take all these archives of satellite images, park our algorithms in the cloud, and process images not in the hundreds, but in the scale of thousands of images here. And we can look at an entire archive of satellite imagery and be very selective about which images we use, which pixels we use, and then how we process it. Because then we can look at not just looking at the individual red, green, blue bands, but there's also alternative ways to view the color space that actually do enhance the marine environment. Now, that's all in the Red Sea, and I've shown you the Canadian, the Cape Cod, but one of the biggest things about satellite derived bathymetry is every single location is different. Almost every, the environment is different in every location. The amount of light hitting the seafloor is different in every location. So there is no one size fits all best solution. So all these processes and workflows have to be quite adaptable to the local conditions, because there's no sea ice in the Red Sea. So we didn't have a filter for how to automatically filter out sea ice from satellite derived bathymetry until we started looking at the Arctic. And you have to look at narrowing different collection windows for looking at imagery, because obviously when you look at the Canadian Arctic, you can only really use imagery from June, July, August, September, maybe, depending on the areas. So while there is daily imagery and imagery available from Sentinel every 2 to 3 days up in the Arctic where the orbits converge, we really do need a lot of images during these critical months in the summer, because it is such a narrow window. So that's really where, historically, if they went back to the 80s and 90s, was Landsat imagery and trying to look at the Canadian Arctic, getting an image every 16 days. You're just never going to get a good image suitable enough to do satellite derived bathymetry at scale. But as Landsats evolved, as Sentinels evolved, and now Planet and other commercial providers are able to image an area not just once a day, but potentially dozens of times per day at different times, we're able to see the ideal water conditions as they evolve with the tidal periods or the seasonality or wind patterns in a given area. So we're really get under the hood of what images make for the best satellite derived bathymetry results. So what we're able to do, as you can see here in the lower left, you can see that depending on the time of year, you can get all ice, or you can extract out clear water pixels from these satellite images. And that's extracting out individual pixels from individual images, not the entire image. So we're able to look at pixel by pixel. And that's where I think hydrospatial really becomes interesting, from that remote sensing to the hydrography, and you're taking pixels and radiometric qualities viewed from space and calculating hydrographic information in a spatial context. So, and as you can see here in the Canadian Arctic, we can just evaluate these in kind of an automated way based on the spectral reflectance to identify areas, individual pixels that contain ice, or turbidity, or low turbidity, which would mean good conditions for satellite derived bathymetry. And ultimately, there are significant gains to be made in the Canadian Arctic. I always like to point out that 40% of the world's, yes.
3-minute notice.
Perfect, thank you. I always like to point out that 40% of the world's coastline is Canadian. It's an awful lot of shallow water areas to survey, and challenging areas at that, given the environmental conditions and the remoteness of it. So these multi-image and multi-algorithm approaches can really be significantly leveraged in these areas, non-traditional satellite derived bathymetry areas, these challenging areas like the Arctic, because obviously historically you look at a lot of research papers and a lot of satellite derived bathymetry is around the middle latitudes where you get clear waters and bright sun. But now with these evolving technologies that we've developed under our NSF and NOAA grants, we're able to deploy these in much more challenging conditions to meet the needs of the modern world. So we've come a long ways since the 1970s. And we're now in the era of the decade of ocean science, and I see it as the era of scalability of satellite derived bathymetry. We're also entering an epoch of artificial intelligence that we're deploying towards satellite derived bathymetry, which is an exciting acceleration of these technologies. So I think it's a technology that's coming of age at just the right time to meet these needs for seabed 2030 and the UN decade of ocean science. So what do we see next in satellite derived bathymetry that's really the next game changing? Hyperspectral imaging, in my opinion, is going to be a significant driver of the technology in the coming years. And then also technology to be able to co-collect imagery with hyperspectral, multispectral video, and potentially more green lasers. I think is going to be a really interesting development in the coming decade. So that's materials that I've provided. I've also I have a question here for the group that I've always been kind of curious about the Gardner's hype curve around technologies, and always where satellite derived bathymetry is on this curve. So I was curious what other people think where we are in the development and implementation of this technology. And with that, I'm happy to take questions and comments.